Once again welcome to MSB lecture series on main group chemistry. In my previous lecture I started discussion on graphite and single layers of graphite, it is called graphene, and how to generate carbon nanotubes from graphene. So, let me continue from where I had stopped. The structure of carbon nanotube, also known as NCT, can be imagined as a cylinder formed by rolling a graphene sheet and then closing it on both sides by Fullerene hemispheres. So, that means essentially if it is a graphene single sheet, graphene single sheet I had mentioned, this is graphite, and then if I could take out very effectively single sheet, this is nothing but graphene, and this graphene by folding, and I can have a cylinder, it is called graphene cylinder. Graphene can be cut into thin stripes or nano ribbons by lithographic techniques. These ribbons are described by their edges, either zigzag or armchair. One can join the edges of nano ribbons together to form such nanotubes in several ways. It can also form multi-layer carbon nanotubes in which one layer have pi interaction with another one. So, you can also have concentrated nanotubes of having different diameters. So, you can see here carbon nanotubes here, as I mentioned, when we fold a graphite sheet, we can complete it by clipping these exposed carbon atoms in this fashion. This is called zigzag, or one can also make in this way. This gives a chiral center, or one can also make like this armchair, something like this. So, there are several ways in which the clipping of the edges can be performed. So, this is how a typical carbon nanotube looks like. And if I could take a smaller nanotube, put it inside, you can see this one. One can play around. These are called multi-layer carbon nanotubes. So, let us look into another important compound of graphene, that is graphene oxide. Graphene oxide, formerly called graphitic oxide, is also called graphitic oxide or graphitic acid is a compound of carbon, essentially carbon, oxygen and hydrogen in variable ratios. By the oxidation of graphite or graphene using strong oxidizing agents, oxygenated functionalities are introduced in the graphite structure, which not only expand the layer separation, but also makes the material hydrophilic. You should remember graphene or graphite is hydrophobic, but adding these oxygenated functionalities, one can make the material hydrophilic. Graphite oxide is a multi-layer system, whereas in a graphene oxide, dispersion of few layers or monolayers flakes can be found. That means, dispersion of few layers or monolayer flakes can be found, something like this. Of course, one can also put epoxide here, or hydroxyl groups can be added, or carbonyl groups can be added, or even carboxylic groups can be added, and you can see here. And now, this is how the dispersion of these groups can be visualized on a single graphene sheet. You can have all kind of oxygenated functionalities on the surface of graphene. Let us look into other allotrope of carbon, that is diamond. Diamond is a metastable allotrope of carbon, in which the carbon atoms are arranged in a variation of the face centered cubic crystal structure called a diamond lattice. In fact, in carbon what happens, every carbon atom is tetrahedral and coordinated to another carbon atom, and this network is three dimensional in nature, that leads to the formation of diamond. So, diamond is one of the hardest substance known. The major industrial application of diamond is in cutting and polishing tools. And this is how the diamond looks like. So, every carbon atom is binding in a tetrahedral fashion to neighboring carbon atom, and this network grows in 3 dimension to give this kind of structure here. Okay. Cubic structure of diamond can be seen here in this diagram. Okay. So, let us look into the difference between graphite and diamond. Density is more in case of diamond, it is 3.513, whereas graphite 2.26, and electrical resistivity is remarkable in case of diamond 10 to the power of 11, whereas in case of graphite you can see that, and standard molar entropy is 2.377 in case of diamond, whereas in case of graphite it is 5.740 joules per mole per Kelvin, and carbon-carbon distance is much longer in case of diamond, it is 154 picometer, whereas in case of graphite it is 141.5 within the layer, and between the layer the separation is 335 picometer. Another important allotrope of carbon is fullerene. It was first reported by 3 scientists, Croto, Curl and Smalley in 1985, and they showed the presence of C60, C70 as well as C80. A fullerene is a molecule of carbon in the form of a hollow sphere resembling a football, okay, or it can be in the form of an ellipsoid or a tube and can take many other shapes. Fullerenes, also referred as Buckminster fullerenes or buckyballs, as it resembles the ball used in association football. Cylindrical fullerenes are also called carbon nanotubes, bucky tubes. Fullerenes are similar in structure to graphite, which is composed of stacked graphene sheets of linked hexagonal rings. Unless they are cylindrical, they must also contain pentagonal or sometimes heptagonal rings as well. You can see here fullerene. So, it is made up of hexagonal as well as pentagonal rings, and also you can see here it is made up of 6 membered as well as 5 membered rings. So, just let us look into one point here. The melting point of diamond and graphite are greater than 3550 degrees centigrade, but carbon 60 sublimes between 450 degrees centigrade to 500 degrees centigrade. Why is this difference? Melting point of diamond or graphite is greater than 3550 degrees centigrade. Only carbon atoms are there. In C60 also only carbon atoms are there, no hydrogen atom or anything else, but here it sublimes at between 450 to 500 degrees centigrade. So, that means here one should remember what is the meaning of melting point, and in case of graphite or diamond, melting point means the cleavage of all the bonds associated with diamond. So, that means we have to strip off all the carbon and we have to take individual carbon atoms. When we achieve the separation of each carbon atoms, it indicates we achieved melting point. Whereas in case of C60, C60 is a molecule something like this, and in solid state they are arranged in this fashion through some weak interactions. In melting point what happens, essentially we are separating them. So, they are held by weak interactions, as a result it sublimes at 450 degrees centigrade, whereas in case of graphite if we have something like this, if it continues every bond has to be broken, and same thing is true in case of a tetrahedral carbon atom. So, here essentially we have to we have to strip off all carbon atoms from each other to achieve its melting. Same thing is true in case of fullerene. Essentially we have to take out this, because this itself is a molecule. So, this is the difference between the melting point in case of diamond, graphite and fullerene. So, I have shown you some fullerenes. C20 and C24, C28, C36, and also here this is essentially fullerene in which 12 carbon atoms are replaced by 12 nitrogen atoms. This is a C48N12, it is a heterofullerene, and C50, C60 and C70. These are some of the important fullerenes. Okay. And let us look into the reactivity of fullerenes. Fullerenes are formed when an electric arc is discharged between carbon electrodes in an inert atmosphere. Although C60 exhibits a small degree of aromatic character, its reaction tend to reflect the presence of localized double and single bonds. For example, if that is the case, if any olefin having a double bond undergoes addition reaction, you can anticipate similar addition reactions in case of fullerene also. In fact, it undergoes addition reactions. The ene-like nature of C60 is reflected in the range of reactions such as the addition of an oxygen atom to give an epoxide, or addition of ozone at 257 Kelvin to yield an intermediate ozonide like C60O3, or reaction of C60 with free radicals also can readily occur. So, polyhedral fullerenes undergo reversible multi-electron reduction and form complexes with D-block organometallic compounds and also with osmium tetroxide. Let me show you some of these reactions here. Let me write some reactions of C60. Okay. For example, if it is treated with F2 at 343 Kelvin for days, it forms C60 F60. Okay. Similarly, ICl is added in benzene at 298 Kelvin, it forms C60 Cl6. Okay. And if you treat with bromine liquid at 298 K, it forms C60 Br24, or with controlled addition of Br2, okay, at 298 Kelvin only in benzene or carbon tetrachloride, it can give you C60 Br6. So, that means by controlling the amount of bromine we are using, we can either make C60 Br24 or one can make C60 B6. Similarly, one can also use Br2 at 298 Kelvin in carbon disulfide or CHCl3 chloroform to get C60 Br8. One can also take fluorine with sodium fluoride at 520 Kelvin, okay, or directly F2 at 550 Kelvin. One can get C60 F46. Okay. This is the major product. Along with this one, one can anticipate C60 F48 in about 10 to 15% yield. So, this indicates some of these reactions of C60 with halogens. One can also perform, as I mentioned, addition reactions. For example, I would mention something like this, C60. Okay, one can conveniently mention like this. So, this one simply, if you add ozone, okay, one can generate something like this. Something like this. And of course, once after making this one, if it is exposed to UV light, O2 comes out to form oxide, epoxide, okay. Or one can take this one and treat with heated to 296 Kelvin, okay. O2 can come out here also, and one can also get, now it will be something like this, it will be part of it, it will be, okay, it opens up one CC bond, it forms, or it can be simply an epoxide, something like this it can form, okay. And taking C60 directly, let us say if we treat this one with this reagent, okay. Okay. So, N2 will come out here. So, here one can see addition reaction happening here. Okay. So, it is diazo compound can be taken and added, so that you can carry out several reactions, okay. Of course, one can also add carbonyls also onto it. You can see here some of these reactions are shown here in this one, okay. You can take these radicals and you can add it here, or you can take RuCO3 fragment, okay, or you could take Ru3CO12, you can do addition reaction in this fashion, okay. And also one can treat this one with osmium tetroxide in presence of pyridine to form a compound of this type, okay. So, these are all reactions are very similar to reacting some of the species with a single alkene. That means, essentially they resemble the reaction with an alkene or as simple as ethylene molecule, okay. So, let us look into the catenation. Catenation is very common for carbon, then for silicon, germanium and tin among group 14 elements. The much higher CC bond enthalpies compared with those of silicon, germanium and tin means that the formation of compounds containing bonds between carbon atoms is thermodynamically more favorable than analogous compounds having silicon, germanium or tin bonds. On descending group 14, so orbital overlap becomes less efficient as the valence orbital size increases and they become more and more diffuse, okay, as the principal quantum number increases. For this reason, what happens is catenation is less pronounced among heavier group 14 elements. The backbones of saturated hydrocarbons are composed of CC bonds, that is their formation depends on catenation being favorable. An additional factor that favors the formation of hydrocarbon is the strength of CH bonds. So, stronger than SiH, germanium hydrogen or tin H bond. So, carbon hydrogen bond is much stronger than any of the hydrogen bonds of the group 14 elements. So, when we look into the catenation, catenation can lead to all kind of polymers in case of carbon, whereas in case of silicon it is restricted to having 10 silicon atoms in the chain, for example, Si 10H22 for silicon, and in case of germanium one can go up to only 9 germanium atoms in a chain, germanium Ge9H20 for germanium, and in case of tin only dimeric compound is known very similar to ethane. And of course, in case of lead with great difficulty using very bulky groups one can kinetically control and make a dimeric species, okay, having some multiple bond character, okay, something like this. Of course, here the structure of this one is very interesting and I will be explaining the structure of this one, how this PB distance, it is not actually a double bond, but it has a double bond character. It is not a conventional pi bond that we come across in case of carbon-carbon. It is a different one that I would be explaining those things when I go to the organometallic chemistry of group main group compounds, and especially while comparing the bonding of tin compounds with lead and other silicon compounds having more than one bond or multiply bonded main group elements. So, this is one example of a dimeric lead compound. Of course, you can see here this PB-PB double bond is stabilized by very bulky groups. We have 2,6-diisopropyl phenyl groups. Okay. This is kinetically, this PB-PB bond is stabilized. Okay. So, sulfur 2 catenates, of course, when we look into the catenation, another element in the main group or among the elements in the periodic table that forms a larger number of catenated compounds is sulfur. The first one is carbon, second one is sulfur. Of course, I will be discussing more about this sulfur chemistry when I start discussion on group 16 elements. Nevertheless, let me compare its catalytic abilities since we are talking about catenation of carbon. So, the great variety of molecular forms can be achieved by sulfur bond formation or catenation of SS. Numerous way in which the molecules so formed can be arranged within the crystal. SS bonds are very variable and flexible. Bond distances can vary from 180 to 260 picometers. There is some elasticity is there in the SS bond in catenated compound because of single to multiple bond character. Bond angles can also vary from 90 to 180. That is another interesting feature. Not only the bond angles, even dihedral angles can also vary from 0 to 180, and estimated SS bond energy is 430 kilojoules per mole, and the unrestrained SS single bond energy is 265 kilojoules per mole. So, less tendency to stabilize SS bond similar to OO bond, but they are not as stable as carbon-carbon bonded compound. Nevertheless, it shows moderately stable catenated compounds. So, catenated halides are another important class of compounds similar to extensive range of hydrocarbons. Diverse range of halocarbons are known, especially chlorocompounds, fluorocompounds as well as fluorochlorocompounds together. Best example being polytetrafluoroethane, that is also called PTFE, an extremely stable polymer finding numerous applications, and this PTFE has something like this, the structure. Okay. It goes and all are fluorine atoms. This is called polytetrafluoroethane. Okay. So, PT. For silicon, a large number of higher halides are known containing chains of silicon atoms analogous to the polysilanes. Germanium, tin and lead form few analogous of the silicon compounds because of the lowest stability of EE bonds going down the group and the increased stability of the divalent halides. Let us look into the hydrides of group 14 elements. The group 14 elements form tetravalent hydrides CH4 with hydrogen and carbon and silicon form catenated molecular hydrides. Okay. So, that means we can see catenated hydrides as well. Of course, hydrocarbons are essentially catenated hydrides. In case of silicon also we can expect that one having a chain length of 10, okay, having up to 10 silicon atoms in the chain, and each one is having 2 hydrogen atoms. Okay. The relative strength of a CH bond compared to CCl and CO bond, and this trend is not mirrored by later elements. CH4 is chlorinated with some difficulty, whereas SiH4 reacts violently with chlorine. Okay. CH4 is very stable with respect to hydrolysis, but SiH4 is readily attacked by water. Here the reactivity of SiH4 is purely kinetic. SiH4 is spontaneously inflammable in air, and although it is the kinetic stability of CH4 with respect to reaction with oxygen at 298 Kelvin that is crucial, the values of delta C H naught shows that the combustion of SiH4 is more exothermic than that of CH4. As I said, one is exothermic, another one is kinetic. Okay, I shall explain later when I talk about the reactivity of SiCl4 with respect to CCl4. CCl4 is not prone to hydrolysis, whereas SiCl4 can undergo readily hydrolysis. Okay. So, in addition to their inherent kinetic instability, silanes are difficult to handle because they are very reactive. For example, if you take here, this is a typical reaction of a carbon hydride or hydrocarbon reacting with oxygen to give water and carbon dioxide. Similarly, if we compare the reaction of silane with oxygen, it gives silica, that is SiO2 plus water. So, in fact, both the reactions are thermodynamically favored to proceed towards the right. Okay. The major differences not apparent in the stoichiometric reaction is the energy of activation, which causes the paraffins to be kinetically inert in contrast to the relative silanes. Further complications with silanes arise from lack of conventional synthesis and difficulties in separation. However, compounds N equals 1 to N equals 8 have been isolated, including straight chain as well as branched chain silanes. Of course, more details are given in this book. I will stop at this stage and I will continue the discussion on hydrides of group 14 elements in my next lecture. Until then, have a pleasant reading of inorganic chemistry. Thank you very much.